Hello and welcome to the course of Advanced Strength of Material. In this course, so far we have studied about strain energy, and that is our first chapter or first module. And in the second module, we have talked about bending stress and shear stress. In case of module 2, we have we have studied about we have studied about bending equation. So we have seen bending equation, we have seen the theory of simple bending, we have seen the assumption of simple bending, and we have derived an equation for our we have and we will see about section modulus and flexural rigidity. So we have derived the equation of bending using moment of resistance in the last lecture. This is sixth lecture of this topic, and the lecture name in today we are going to discuss about section modulus of different section. So in the last lecture we have discussed about what is section modulus, and then in this lecture we will discuss about the section modulus of different section. We will see about flexural rigidity, what is flexural rigidity, etc. And we will see about the concept of economy section. So let's start with our lecture objective. Our lecture objective here is to derive the section modulus for different section. This is most important lecture objective. We will see the section modulus for different section. Next, we will to get an insight about flexural rigidity, to introspect about the concept of economy section. So concept of economy section will be taught in this lecture. So first let's see the section modulus of a rectangular section. Now in case of a rectangular section, the rectangular section with similar to this figure, which has breadth as b and width as d, and the distance from Na to the topmost or outermost fiber or outermost filament or outermost layer is d by 2. Now we know that moment of inertia of the rectangular system is given by b d cube by 12. This is the rectangular section about what? About this axis, about this centroidal axis or centroid or neutral axis. So and y max is d by 2. Now we know the section modulus is the ratio of moment of inertia to the distance of outermost layer from neutral axis, that is y max. So z by y max is our section modulus. So if we put the value of I and y here, then what we will got? We will get b d cube by 12 by d by 2. Now by d by 2, if we simplify it, it will be like this: b d cube by 12 into 2 by d. This is a simple, this is very simple division. So by division, what we will got? This d cube d will cancel out, and it will give us b d square, and 2 and 12 will cancel out, and this will give us 6. So that gives us the equation z is equal to b d square by 6. So z for section modulus for rectangular section is given by b d square by 6. This is the section modulus of what? A rectangular section. So for rectangular section, the section modulus will be BD square by 6. Similarly, let's see for a hollow rectangular section. Now for a hollow rectangular section, the moment of inertia will be I is equal to B, capital B d cube, where the capital B is the breadth of outer rectangle and capital D is the depth of outer rectangle. Similarly, small b is the breadth of inner rectangle, and small d is the depth of inner rectangle. Now, if we do the moment of inertia will be b d cube by 12 minus capital B d cube by 12 minus small b d cube by 12, and distance of outermost layer, the distance of outermost layer, see from this neutral axis, the outermost layer from this neutral axis, the outermost layer will be here in the at the D2, that is capital D2. So y max is given by capital D by 2. Now section modulus, similarly I by y max, that would give us 1 by 6 d I by 1 max. Then if we put the value of I, this value of I is put on the numerator, and this y max value is put on the denominator, and by this if we take common 12, then it will become 1 by 12, it will become 1 by 12 1 by 12 b d cube, capital B d cube minus small b d cube. So that will be here, and here it will be 2 by d. Now capital D won't be cancelled out because it is inside the bracket, and so the equation will be, or the section modulus can be given by 1 by 6d b capital B d cube, this capital B d cube minus small b d cube. So this is the section modulus for a rectangular hollow section. Now section modulus for a circular section can be find out on a similar manner. So for circle also, first we have to calculate the moment of inertia about center of gravity, or moment of inertia about neutral axis. And this moment of inertia will be, for a circle, the moment of inertia is always be pi by 64 d to the power 4. Now distance, so for the circle also, this is the circle, and neutral axis will be here, and neutral axis will be through the center. So for outermost fiber, distance of the outermost fiber will be small d by 2. So y max is similar to previous two cases, that is small d by 2. And if we calculate here, 2 can be cancelled out with 34, with 64, that would give us 32, and d can be cancelled out with d to the power 4, that would give us d cube. So the equation will become pi by 32 d cube, Now for hollow circle, what will happen? For hollow circle, the moment of inertia of a hollow circle will be given by pi by 64 capital D to the power 4 minus small d to the power 4, where capital D is the outer circle radius and small d is the inner circle radius. Now the y max is given by capital D by 2. Y max is, you can see from the neutral axis, the distance between the outer layer and the neutral axis is given by capital D by 2, and the section modulus is given by, so the section modulus is given by I by y max. That means this I by d by 2, means into 2 by d, now this 2 will cancel out, this 64, and 32 will be remained. So this 32 will be multiplied with d. This 32 will be multiplied with d to the final answer, that will be pi by 32 d into d to the power 4 minus d to the power 4. So this is the section modulus part, and next we will see the some practical application where the bending equation or bending equation can be used practically. So bending equation is applicable to the beam which is subjected to pure and simple bending. So only the case where only the bending moment is there, then we can use this bending moment equation. So in the case of bending moment is acting, that means when only pure bending moment is there, that means the shear stress is zero and the bending moment is constant. Bending moment is constant. So, but in practical case, that is rarely possible. So bending moment always varies from section to section, and shear force is not always zero. But in some section where the bending moment is maximum, in some section where the bending moment is maximum, at that time shear force can be zero. So that's why bending equation or theory of bending can be applied for the cases where bending moment is maximum. Why? Because as the bending moment is maximum, shear force is likely to be uh, zero there. So if there is no shear force, then the bending is pure bending. So that's why we use beam and structure. The beam and structure that are used in day-to-day life is checked on the basis of maximum bending moment. So let's see about after knowing that, let's see about flexural rigidity, or flexural stiffness, or flexural resistance. What is it? So for till now what we have said, that for pure bending, uniform section, beam will deflect into circular arc. So from the equation of pure bending, or from the theory of pure bending, we know that for pure bending, the uniform section of the beam will deflect into the circular arc, and for this the term circular bending is given to the bending pure bending case, and this radius of curvature of this bending can be given by R is equal to E by E into I by M. This equation is coming from the bending equation that we have derived earlier. From that bending equation, this equation is coming. Hence, so that's why from this equation, what we can see that this radius of curvature R is directly proportional to what? EI. So this radius of curvature R is directly proportional to EI. Now, since R means what? R is the direct degree indication to the degree of flexibility. R is direct indication to the degree of flexibility, and so that means if the R is less, beam is more rigid, and if R is large, then beam is more flexible. So R is the, or so radius of curvature is the index of degree of flexibility. So that's why flexibility depends on the flexibility depends on the radius of curvature. So that depends on EI. This E into I is known as flexural rigidity or flexural stiffness of the beam, and the relative stiffness of the beam section can easily be compared with this EI value. So this is flexural rigidity. And now in economy section, what is economy section? So from the bending equation, what we have known, from the bending equation we know one thing, that is sigma is equal to our sigma, that is from the bending equation we know the sigma, that means bending stress is equal to m by y, is equal to my by I, and this is coming from the bending equation. And so in the neutral axis what is happening, this y is increasing from the neutral axis towards the wall. Now in the neutral axis uh, y is 0, that give us bending stress value is equal to 0. So which is increases, so bending which increases linearly outward. So that means the rectangular or circular section, whatever may be the section, of a large in that section, large portion of the cross section near the middle of the section is unstressed, means there no stress will be forming on the middle portion of large shape. So that would a high material loss. And so to overcome this high material loss, concept of economy section is came into culture. In the concept of economy section, what is happening for steel beams or composite beams, what is happening, instead of adapting the rectangular shape, the area may be so arranged so that it give more area on the outer fiber, and maintaining this the same overall depth, and it saves a lot of weight. So economy section means to make a section with necessary modification so that it can be, so that it can be save, it can save a lot of word, it can save a lot of weight. So that is all about economy section. In the next lecture, we will see about the bending moment and bending stress diagram for various sections such as I section and etc. So till now, if you have any problem, so I request you to please ask. Thank you for being here, and we will discuss this topic in detail on the live class. Thank you.